Good morning. Good morning, everyone. So we're going to start with the new plenary keynote. The speaker today is Dr. Professor Narendra Dahotre from the Center of Agile and Additive Manufacturing from University of North Texas. He will be talking about multi-scale, multi-physics numerical modeling of laser-based additive manufacturing. Please give him an applause. And the floor is yours.
Yep. Thank you very much, Hector and Patricia, for inviting me to this conference. This is my first time to Cancun and the first time to attend this conference. When I looked into the agenda, I realized that there is a very broad audience in this conference. Typically, whenever I attend any conference, we attend conferences related to conventional structural materials and manufacturing. So keeping that in mind, I'm going to give you the very broad perspective of additive manufacturing, because additive manufacturing has taken off in last 5 to 6 years, and a lot of people have been working in this area. The people from various backgrounds and various interests have started working in this area. So with this situation, people come from various backgrounds. Some of them are design engineers, some of them are mechanical engineers, some of them are materials engineers, and so on. So the additive manufacturing has two main components. One is an instrument which manufactures the component, and second is the material which get manufactured by using this technique. So there are two things combined, get together, and a wonderful product comes out of it. So what happened in the additive manufacturing is people working from the manufacturing side, they have put a lot of efforts in designing the manufacturing process, automation, then motion system, and so on, which allows us to create very complex shapes and sizes in the component. And there are people working from the material side. They work on the material to study the material which get printed. After printing, what are the properties of the material? Functional, structural, all kind of properties they study. But there is a disjoint between these two communities. What happens is the people who are experts in manufacturing, people who are expert in material, but none of them know how the additive manufacturing converts the material what is being printed. It does not come out in the same manner in terms of its properties or in terms of its microstructure as that is manufactured by conventional manufacturing technology. Conventional manufacturing technology has been in existence for last several decades, close to 100 years, and it has evolved so well that we have designed the manufacturing processes, conventional manufacturing processes, to produce the component with desired properties. It has been very well studied. But in additive manufacturing, there is a disjoint. People work on the manufacturing part very well, but they don't understand that manufacturing process, what produces, is of any use, or does it have the same properties what that component is intended for, for the application. And materials people, all they do is a printed component. They just test it after the printing, what has come out of it. But none of them know how to control the process to get not only shape and size in the component, but the required properties in the component. And that is what I'm going to introduce to you. My background is laser materials processing. I have been working in laser materials processing for last 40 years, you can call it. And my also background is in hardcore structural materials and the phase transformation in the material. So because of this unique background, I have learned a lot how the laser interacts with the material, how we can control the laser to control the evolution of the microstructure in the material for the intended properties. And the additive manufacturing, as you know, most of the additive manufacturing processes laser is the heat source. There are few additive manufacturing processes where you can use the electron beam, where you can do the additive manufacturing by friction stir additive manufacturing process, where you don't need the laser. But most of the powder-based process, powder bed-based process, direct energy deposition process, both involve mostly laser as a heat source, because that is the only intense heat source which can instantaneously melt the material to make it as a liquid, which is equivalent to ink in your inkjet printer. And that liquid is then printed on your substrate material. So first you have to create a ink or liquid out of metal, and then inject it on the substrate in a controlled fashion to get the required component printed out. So only laser is the intense source which can melt any material, especially metals and ceramics, instantaneously to convert them into liquid, and then you can print them on the substrate. So as I just said, that process is very intense. High energy beam, laser beam is used, and you deposit and cool it down instantaneously. So it's a very rapid process. Under the rapid thermokinetic process, the material evolves with a very different microstructure, different phase structure. And one has to understand. Means if I give you an example, if you take a gear, conventional gear you use in any machine, any machine, and if you manufacture that gear by conventional manufacturing technology, which involves several processes, cutting, welding, drilling, milling, grinding, and so on, and then in the end you get a gear, and then you heat treat that gear to get the required property, which is typically hardness, high hardness, and wear resistance, and so on and so forth. But if the same gear, similar type of gear, if I print it by using additive manufacturing technology, then it is only one-step process. I feed in the powder as a feed material or the starting material, melt that powder, and deposit in a required shape and size, and out comes a gear. So it's only one-step process. It avoids all those things. But it is a very intense, very rapid process. So the evolution of the microstructure within that gear and the phase structure within that gear manufactured by additive manufacturing process is way far different than your gear manufactured by conventional process. That means they look alike, but they will have different properties. So the conventional manufacturing process has evolved so much that we know how to heat treat this gear and get the required properties. Whereas we don't know yet what are the heat treatments we have to design, or what comes out of additive manufacturing to start with as a microstructure and phase structure. Then only with that understanding, then only we can design heat treatment. So that is what we spend our time, quite a bit time we spend. And now again, I have to give one more background before I start showing you my slides. It's very important to have some background. As just now a minute ago, I said that additive manufacturing mostly is a laser-based process, powder bed fusion process, and powder injection process, direct energy deposition process. Both in one process, we have powder bed, the powder set in the tray, and the laser beam comes and moves onto the powder, and powder get fused. The fused powder get covered by the loose powder. Again, you remove the laser beam on it, and you can build a layer by layer a component. So the powder is stationary in this process, laser powder bed process. Powder is stationary, only laser beam moves. Whereas direct energy deposition, or the powder injection process, where the powder is injected into the laser beam, and the laser beam and powder together move, and the powder get melted when it is entering into the laser beam, and the molten powder get deposited. So in this case, powder is moving, dynamic process. So just by these two different characteristics, the thermokinetics involved in these two processes are pole apart, far different. So again, within additive manufacturing itself, if I print the component using the powder bed fusion process, where the powder bed is a stationary bed, powder, and if I use the powder injection process, where the powder is moving along with the beam, the kinetics, thermokinetics, totally different. Temperature attained in the processes are totally different. The kinetics of the process is different. What it means that heating, cooling rates are different. And as you know that, under the different heating, cooling rate, material evolves with a different microstructure, different phase transition, and so on. So this will tell you how important it is to know the kinetics, thermokinetics of the process, and to understand that, to really get a control over the additive manufacturing, one has to understand the manufacturing process and one has to understand the materials part of it. You cannot just live with the manufacturing process as an expert and not worry about the materials. You have to worry about it. And current state of the additive manufacturing is the stage where we are able to print complex shapes parts with the one process using additive manufacturing, but all those components do not have the kind of properties required for the application or for the intended application. Because we work very closely with Defense Department of Defense, work with the Department of Energy. I work with the automotive industry. I work with a lot of energy industry. They are interested in printing their components using additive manufacturing. But if you walk into the production facility of any company, big company, you will find no additive manufacturing machine, AM machine on the shop floor. Yet, all those machines are there, but they are in the research and development section. And the reason for that, they are able to print all those components, but none of those components have the properties required for their application. Nowhere close to that. And that is why all these big companies are stuck in that process. And there are not many research groups or not many people who are willing to help them, not because they don't want to help them. They don't have the background in that area. And that is where our focus is. At the University of Tennessee, University of North Texas, at the Center for Agile and Additive Manufacturing, in other words, we call it a CAM. We focus on this aspect very heavily, and we work with a variety of material system, right? Low melting materials starting from aluminum, magnesium, to all the way to the high temperature materials like nickel-based superalloys, high entropy alloys, ceramics, refractory materials, and so on. All of them have different properties, and they behave differently under these extreme conditions of additive manufacturing. So that is our emphasis. So it's a very broad topic. As I said, that I have spent many years of laser materials processing. My background was in laser-based cladding coating, which is nothing but the core of the additive manufacturing. I have designed the machines 30, 40 years back where I was using laser-based layer-by-layer deposition of hard materials for wear resistance, corrosion resistance, so on. Now all this can be extended into additive manufacturing due to the very sophisticated robotic systems. Now you are able to deposit the material in very complex shapes and sizes, layer by layer. Earlier days, I used to do it only by a simple, straight deposition on the simple components, shapes and sizes of the component, and so on. So we have tremendous background in that area. So it is a very broad topic. It deals with a broad number of techniques and number of materials. So what I decided, I'm going to give you some example, which is related to the H13 steel, which is a tool steel, which has a lot of applications in real life, and it is very unforgiving in terms of processing. When the H13 is processed by conventional manufacturing processes, it is very hard, very difficult to process. It's very hard. It's high temperature materials used for the major uses in the tool dies, permanent die casting application where the tool die is made out of H13. It is very hard and it's very difficult. So it is also difficult to print using AM technology. So we have attempted to work with these materials. I'm going to give the example of that and show you how we approach. I may not be able to go into a greater depth, because this whole work is over the period, conducted over the period of several decades. So I'm going to give you just a snapshot of how we approach this process. So H13 still, because I want to, before I show you how we use the computational modeling to control the process and the outcome of the process, that means how to control the evolution of microstructure and phase transformation in the additive manufacturing. To know about that in general terms, you need to know, and that is being applied to H13 printing, H13 steel printing. So you need to know what are the H13 characteristics are. As I said just now, H13 steel is a high, it's very difficult to manufacture, especially with AM technology. It has a very good high temperature mechanical properties. That's why it is used as a permanent die molding, die casting mold. Aluminum, most of your car engine, aluminum car engine is cast by using this H13 molds, or many other automotive parts are cast, aluminum parts are cast using H13 tool steel. So it's very expensive material. I work with a lot of automotive companies. The dies are very large dies, especially when you cast the aluminum engine, your car engine, which is pretty big one, 4-cylinder, 6-cylinder, 8-cylinder car engine. So die is also very big. And there are several other components also cast out of aluminum using the H13 die. So the molten aluminum is poured into this die, and the casting gets cooled down, and then it's removed from the die. But as you know, automotive industry is a high volume industry. So all these components are produced thousands in a day. So where the way they process this material, the casting is, they pour the aluminum in the die, and then the die moves into the next station where it is cooled by the water spray to reduce the time of the cycle, and then that die is again used for the next casting. So it continuously heated and cooled down in a process, so it has to resist the thermal cycle. So this is a very tolerant material for that purpose. But making the die out of this H13 is very expensive. So over the period of this undergoing through thermal cycle, this die start cracking. They produce surface cracks, and then molten aluminum seeps into those cracks, and those cracks expand, and then they go out of use. And that each die, depending upon the size, costs anywhere from tens of thousands of dollars to $500,000 to $1 million. So oftentimes the industry refurbish those dies by grinding them, welding them together, and so on. So that's where these dies are very important, and that process of making this die takes months and months and months, and very expensive, labor intensive. So AM could be a best technology for both ways. One is to produce this die with a complex shapes, because the die is conventionally made by grinding and milling and so on, so which is a time-consuming process. But AM will be the one-step process to make these complex dies. And if at all, if they fail by cracking or wear, then we can rebuild them by using this additive manufacturing. As you see in the bottom of this, in 1997, these H13 dies were manufactured by additive manufacturing technology. This is actual photograph, layer by layer deposition of H13 done by the Professor Jyoti Mujumdar from University of Michigan. He was the pioneer using the additive manufacturing technology. Those days, that technology was not even called as additive manufacturing technology. I know him pretty well. That time I was a graduate student and used to visit his lab, so I know his whole operation. So as earlier in late 90s, this technology was used to produce H13 dyes. So there are few efforts in the literature which shows that these H13 dyes were made using high energy source high energy source beam by using the additive manufacturing technology. So there are people who have used electron beam along with the laser to deposit this H13 or to manufacture these H13 dyes. Now, if you use the laser beam technology, as I said earlier, involves very short time. Typically, the interaction time of the laser with the material is less than milliseconds, sometime in nanoseconds, and so on. And what happens is time is very short, interaction zone is very small, because laser beam is typically used in this additive manufacturing process is few microns in diameter. So time is short, as well as the interaction zone is smart, very small. So what happens is this process, monitoring this process is very difficult. If you want to do any in situ diagnostic to see what is going on in the region of the laser material interaction, such as you want to measure a temperature, you want to look at the fluid flow characteristics in the laser material interaction zone, it is very difficult. And that is difficult is because too short a time and too small a zone, and there are not many in situ tools which can respond to this kind of extreme conditions. So you cannot use the typical infrared cameras to measure the temperature because it's very intense at the laser material interaction zone. Oftentimes, it produces the laser metal plasma, and it obstructs the view of your infrared camera, and whatever you measure gives you erroneous results in terms of temperature. If you use any acoustic techniques, the time is so short that sensors have oftentimes slow response compared to the process time. So you cannot use the acoustic sensor, you cannot use the optical sensors, and so on. So it's very difficult to monitor the AM processes. So only way you can do this process predictions or understanding of this process is computational modeling. And in addition to these extreme conditions, thermophysical conditions, this process becomes more complex. The AM process becomes more complex because, as you know, that laser being a very small beam diameter, you cannot fuse only small portion of the material. So you have and laser. So with that, you have to create a layer by putting multiple tracks in one layer. And then you have to deposit several layers to create a component of reasonable size and shape. So it is a multi-track, multi-layer process that creates a very complex thermokinetics in the process. And thus the process becomes very difficult to monitor, or to control, or to get the understanding of the process. In literature, if you look into literature, people have tried to model this process to get better understanding, but most of the modeling is confined to either multi-track single layer, or single track multi-layer or single wall process. So what they do is they model the process of the only single layer, which will have multiple tracks put in the single layer, and they model that process, or they will have one track, and that track will be built by multiple layers. So it's a single layer, a single wall process is modeled. None of these two conditions come close to a multi-track, multi-layer process, where the thermokinetics is way complex than what is projected by these two approaches. So what our group, or we center, what we do is we try to go as close as possible to this situation. So I'm going to give you some snapshot. So again, I want to go back and emphasize the process parameters involved in the additive manufacturing, especially laser-based additive manufacturing, are laser power, laser scanning speed, that the laser beam, the way it moves, at the speed it moves, beam diameter, then the hatch spacing. Hatch spacing is the spacing between the two tracks put next to each other, and the scanning strategy. I will talk about scanning strategy in next few slides. These are the major parameters associated with the laser-based AM process, and that produces the material after printing by going through the certification. It produces the depending upon this combination of these parameters, you get a different certification morphology in the printed component. It also controls the state of the phase, because the kinetics of the process will control the type of the phase produced. It also controls the crystallographic texture depending upon the thermokinetics of the process, and it also sometimes brings in the defects in the component, because the process is so rapid that it freezes the material and leaves behind sometime porosity, and also it controls the grain shape and size, grain morphology. All these things are affected by the combination of the parameters chosen during the AM printing. So as I said earlier, most of the people either understand this well, or some other people understand this well, but there is no connection between these two. And that connection is very difficult to develop by any experimental method. So you have to go through the computation of the thermokinetics of the process. So what it means that you have to look into the peak temperature developed in the process, thermal cycles, because the thermal cycles are produced during the single layer, and also when you make the multiple layers, more thermal cycles are created. So that very complex thermal cycles are involved. Then associated with that is thermal gradient, solidification rate, heating rate, and cooling rate. All these things will depend on this process parameter combinations, and that will control the solidification morphology. So currently, most of the groups work in this area or this area, but there are very few people have a connection between these two through this understanding. And as I said, that this understanding of thermokinetics of the laser-based AM process can be developed only through the modeling process. And again, I have summarized here. Single laser track gives only single cycle, thermal cycle, so the single heating and cooling events involved in single laser track process. But actual laser-based AM process involves multiple tracks, multiple layers, and it involves multiple thermal cycles, multiple heating, cooling events, and you have to worry about the thermokinetics. So most of the modeling is in this area. There is very little modeling in this area because it's very complex. So if you want to model the process, AM-based process, you have to do the computational modeling, very advanced level of computational modeling of the process. So let me give you quickly how we connected this experimental observation with the computational modeling and prediction of the microstructure based on the computational modeling. So just as an example, as I said, that we use the H13 steel material to deposit a simple cubical block, and these are the process parameters we use. We kept the power of the laser beam constant, and we varied the speed. Diameter of the laser beam is same, so variation of speed gives you the variation in the laser input energy, which is given in here. and speed controls the kinetics of the process, how fast the beam is varying, So you are varying the energy input as well as you are varying the kinetics of the process, and each one will produce a different kind of microstructures. The way this direct energy deposition process, we did not use the powder base, but we use a direct energy deposition process where the powder is injected coaxial to the laser beam, and both will move together in linear fashion back and forth and create one layer, and then you deposit another layer and so on. Now, when you deposit the material layer by layer, if you move the laser in the same direction, one direction, then what happens? The grains which grow from one layer into the another layer, they will continuously grow as epitaxially in an elongated fashion. So if you cross-section this, if you rotate this, if you move this beam in a linear fashion in the same direction, then the grains which are grown in the block or in the components will be very long elongated grain, because the process is very rapid. Before the bottom layer cools down, the second layer get deposited on it, and it start growing epitaxially on the top of the grains in the bottom layer, and you get a long elongated grain starting from the bottom layer to the top layer, and that is not a good situation. Then your properties are very dependent on the elongated grains. They are very poor in creep and fatigue response is concerned. So you want equiaxial grains and grains which are oriented in different direction to get the uniform properties in the material. To avoid that situation, there are various scanning strategies, which I mentioned earlier in this slide, scanning strategy. So that scanning strategy is, one is either you go in the same direction which produces the elongated grain. If you don't want elongated grain, then we scan the beam in one direction in one layer, rotate it through 90 degrees, and scan in the another direction in the second layer, and then keep repeating that alteration of the scanning direction from layer to layer. And that way, what happens is you create a disruption of the epitaxial grain growth through the layer, and you get a little bit better distribution. There are much more complex strategies also can be used. You can change the bidirectional scanning in one layer, that is going in this direction, coming back in this direction, going in this direction, coming back in the direction. So bidirectional strategy can be used in one layer, and then do the same thing in a 90-degree rotation, another bidirectional scanning, and that way you can start breaking the grain growth across the layer and get much more better equiax grains and so on. So there are a lot of ways you can control the grain structure, but in our experiment, we did only 90-degree rotation, orthogonal rotation in a uniaxial scanning direction, to understand the process. So this is more this is the same thing shown here. This is how the scanning is done in each layer, rotation through 90 degrees. So the computational approach developed for this kind of process involves two steps. One is a macro scale model, thermal model, which involves the prediction of multi-track, multi-layer time, multi-layer effects, and mesoscale, which is more confined to the thermofluidic model predicted in the melt pool, because the material melts and then solidifies. So within that melt pool, what happens is predicted by mesoscale, and that is repeated in a microscale from layer by layer, from layer to layer process. So this thermokinetics model is divided into two steps. One is a mesoscale and one is a macroscale. Mesoscale talks about the grain growth within the one track, and then my macro scale talks about the grain growth or phase transformation across the layers. So, general, these are very complex model. I'm just giving you some key equations, and I'm going to talk about the effect of those. Basically, this is a very standard fundamental transport equation. Then you have heat losses due to the radiation and connection when the laser beam interacts with the material and start melting and solidifying the material. Then the heat of the interaction is lost by the radiation and convection, which are predicted by these equations. And now the heat source for laser direct deposition, as you know, that laser direct deposition, a powder injection process which we are using, has a different equation compared to the steady state powder bed aim process. So you have to formulate the equation accordingly. One thing you have to keep in mind, in this process, we have used the Gaussian beam distribution in the laser beam. Energy distribution of the laser beam is in Gaussian form, so that equation is incorporated here. And that is combined with the powder injected in here. So heat source for the powder is added here, and then which will be different for the powder bed if you use the powder bed aim process. Now this will let me go back here. This will predict most of the liquid pool effect, what the temperature is developed, what is the thermal gradient in the liquid pool, and so on. Whereas if you move on to the next one, what happens is once the liquid starts solidifying, the temperature is still high, and it goes through the cooling from high temperature to low temperature during the solid state form. And during solid state, most of the materials undergo phase transformation. So the final effect, the final microstructure and final phase structure depends not only due to the effect of the melt material, what happens in the molten material, but also what happens after the molten material becomes solidified and how fast or how it cools, what are the thermal gradients are developed in that solidified material will decide the phase transformation. So there are a lot of strain induced base phase transformation in the material. For example, a lot of phases do occur in a solid state transformation. So all those effects can be covered in these kind of equations. These are very generic equations I put in here, and these equations should be solved by using the let me go back a little bit. Using the material properties. Oftentimes, to solve this equation, you need the thermophysical properties, and especially thermophysical properties dependent on the temperature, because it goes through the melting temperature to all the way to the room temperature. So if you have the more detailed properties, values of these different properties, the more accurately you can predict the microstructure evolution in the process. Now, one thing I want to show you here, I'm just giving you a broader snapshot. What is important to look for in this model-based predictions? One is with these models, you can get the solidification rate, you can get a thermal gradient, you can get a cooling rate, and you get a morphology factor. So solidification rate will control how large or small the grains are formed within the final structure. Thermal gradient will give you how the grains grow, in what direction they grow, and what is the crystallographic texture will they produce. Cooling rate will again decide how fast the material is cooling down from the liquid to solid and within the solid state. And that will decide grain size, shape, as well as the phase transformation. And the morphology factor is, again, whether the grains will be elongated, equiax, or something in between. So all these parameters which come out of this model will decide what kind of microstructure or grain structure and what kind of phase transitions or phase transformation will take place in the material. So for example, your laser is moving in. There are 3D depiction of the melt pool and 2D depiction of the melt pool shown here. The laser is moving in this direction. So the velocity V is a velocity of laser beam direction. Laser beam motion speed is given by V, and R is the solidification rate. So the R is connected to laser moving direction by this equation. R equal to V cos theta. V is laser moving speed. So the grains will grow in that direction. The grain growth direction is connected. Theta is the angle between these two parameters, solidification rate and scanning speed direction. The angle between these two is the theta, and they are related this way. So the grain will grow in that direction, depending upon how fast the beam is moving and how fast the solidification rate is happening. So they will control how the grains grow within the melt pool, whether they grow straight up or go in angle or go in horizontal. Everything depends on the values of these one, and these are connected through the earlier equation, through earlier equations. So there are a lot of assumptions you have to do because these models are very difficult to develop, and there are not much information available in open literature. So you have to do a lot of assumptions. Those are given here. The melt pool was considered as incompressible. The thermophysical properties are considered as isotropic and temperature dependent. If available in some materials, you get the temperature dependent properties, or many materials, complex materials, you don't get the temperature dependent properties. Powder addition in the melt pool was assumed to be homogeneous with Gaussian flow distribution. That's why you see the earlier equation. Let me go back. Here also the Gaussian distribution. Powders are thrown into the laser beam, and the distribution of the powder flow is a Gaussian, which is given by this equation, same as this. This is a laser beam energy distribution is in the laser beam, and this is both are Gaussian type. So that is what's considered. Sorry, I'm going reverse direction. That is what considered in the model. And momentum due to the impact of the powder particles on melt pool was neglected. What it means that when the powder get injected into the laser beam, the powder gets particles get molten. They melt instantaneously, but some of the powder particles do not, which are sitting on the periphery of the beam, and they partially melt, or some of them don't melt, and they go down and impact the melt pool. That effect is neglected here. What we assume in this model is all powder particles are melted completely before they go down onto the substrate and form a deposit. So that is considered here. And also, when the powder get injected into laser beam, it is a solid powder initially, so the laser beam get reflected from the particles, and there's a loss of laser energy by reflection and scattering from the powder particle. That is considered as a zero here. We assume that there is no scattering and reflection. So over the period of time, we are developing the complex model which will take into account all these effects eventually. In next few months to a year, we will take this into account. But this particular model does not ignore these effects of the process. So what happens is this is how the one layer is shown. These are the tracks made in one layer. The model, what we do is we we put the electronic probe at one location, and then the tracks are made, and our computational probe is here, which starts looking at the development of the temperature around it. So this is the first track, second track, third track, and the fourth track we get the made on the our computational probe, and then the sixth track passes past this location, and then this location continues to monitor the temperature, and that is plotted here. So this side you get a preheating effect. As the laser beam comes here, it starts hitting these regions, and when it goes past this point, it post-heat this. So the heating keeps going on. Even the laser beam moves from this point away, it keeps hitting this one because of heat conduction. So that is called the post-heating effect. And when laser beam moves from this side to this side, this is called a preheating effect. So the laser keeps hitting the material in that layer while it is going by track. So there is an effect. So the laser moves from this direction to this direction, left to right. While it's moving, it creates the preheating effect. And when it comes to this point, this track, it is the highest temperature here, and it start dropping. So you can generate the heat cycles in each layer, and assuming that this point, whatever temperature history is seen by this point, can be seen by any point in anywhere. That's how we repeat the things. So as you see that under the given condition, at any point in the layer, the temperature around it up to the second, third track drops down substantially. And the fourth or fifth track away from this one, both sides, temperature drops down pretty low. So that is how we track the temperature. So these are the melting. Some of these temperature rise as high as melting temperature, whereas some of them are high enough to cause the solid state transformation within the processing. So look at this cycle. The seen for the one layer from one point, the temperatures are given here. So from this you can see that even the beam moves away from it, still the temperatures created by that beam surrounding this point is high enough to cause the melting in the neighboring track, or the high enough temperature to cause the solid state transformation. So this is for one layer. So look at the multiple layers. You can now this is same. Your probe, computational probe, is at the same point in the first layer, and it is now looking at the heating cycles around it, and also above it when the next layer is put above that one. So here this is a cycle in that layer. Same point is seeing the temperature rise due to the second layer. The same point in the first layer is seeing this cycle due to the deposition of third layer, and so on and so on. So as the top layer is produced, the temperature seen by that point, which was here, is now dropping down, so and so. So this point, in this layer, sees the rise in temperature multiple times, and the magnitude of that temperature rise could be remelting, as high as to cause the remelting here, or sometime not melting, but as high as to cause the phase transformation, solid state phase transformation. So those effects. So how far these effects are valid can be predicted by this computational model. And then if I put the next layer up to here, probably this layer here may not have any effect on this temperature. So now it will be stabilized, and whatever form through these thermal cycles due to the layer 1, 2, 3, 4 will be the one which cause the phase transformation and liquid solid state transformation at this point. After this layer, there may not be probably high enough temperatures seen by this point. So all those things depend on the process parameters and the material properties, and you can predict this point how often and how high it will, high temperature it would experience while depositing these layers, you know. So all this is built into this program, and you can predict the temperature at any point in any layer, temperature cycles, thermal cycles, what it will experience at any point, any layer, you know, and then you can predict what are the phase transformations or what are the grain size or grain development will take place at that point, you know. So let me show you some of the this kind of model. We tweak it or we refine it by experimental observations. Once it is built, what we do is we look at the first thing we do is this is a cross section of the layer by layer depositor block, H13 block. This is a laser beam going into the plane of the beam. This is the one layer. Laser beam is going into the plane in the direction of the into the plane of the board. And this is a second layer where the laser is moving from left to right. Whereas this is another layer where the laser beam is going into the plane of the this screen. Okay, so there are alternate 90 degrees rotation. In this layer you can see the melt depth. This is a overlap region between the two tracks. So the melt depth and melt width is given here. So by those models, we first confirm the accuracy of the model by confirming the prediction of the melt depth and melt width by that model. Once if it doesn't, then we tweak the model to match with these measurements experimentally. And then once it is close enough, then that model is ready to use for the prediction of the all other effects in the material. So that is shown here. These are computational predictions, and these are the experimental measurement of depth and width, and so on. So with this, then what we do is we predict the phase transformation in the material, or the time temperature transformation in the material. You can see these are three different conditions. As I mentioned earlier, the H13 deposition or the AM process was done under three different input energies, 30, 45, and 77. These are the temperature cycles, and you can see the highest temperature, various temperatures, important temperature given here, and these are the temperatures of the various transformation in the material, H13, you know, melting point, then transformation of austenite to martensite, and so on. Those can be easily predicted. And how often that temperature is raised at that point is given by these thermal cycles. You know, these are the thermal cycles at the same point for layer by layer. You know, so in this case, higher energy input, that one point, the point of computational probe, experiences high temperature up to the cycle third layer, up to the layer third. You know, whereas it drops down substantially into layer third in this, under this condition, and it barely reaches high temperature for that point in the third layer, and so on. So whatever transformation occurs in here may not occur in here under these conditions, you know, and those can be major things are predicted in this time temperature diagram for the H13. So these are the transformations, like various transformation can occur outside and inside of these time temperature curves, and those can be easily predicted whether it will happen or not by these computational predictions. So these are given, these are important temperatures and corresponding transformations are listed here for the H13. Again, the same diagram I have given in much better expanded version here. This is layer 1, layer 2, layer 3, layer 4, layer 5, 6, and the kind of temperature it reaches maximum, and so on. And also, it shows that what can happen during these thermal cycles are given by these thermocal-based prediction of the phase transformations. So let me, again, what we did experimentally, we have studied this, what are the phases exist in this process, AM process sample, they're done by X-ray diffraction, and these confirm that these phases do exist at this temperature transformation regimes and so on. This is one good example where I said that the grains, how the grains are evolved in the AM process material. This is the center of the melt pool. You get equiax grains, cellular structure basically, and at the bottom of the melt pool, you get a mostly elongated grains at the bottom of these because the thermal gradient, and if you go by the earlier R equal to V cos theta calculations, you do that, you will see that they are inclined in certain direction compared to the laser motion and so on. So you can precisely predict the growth of this grain, direction of these grains, and based on the G by R factor, you can predict whether they are elongated or equiax and so on. So here are the more precisely, if you calculate the G, which is a thermal gradient, R is a thermal solidification rate, and G by R is a morphology factor that decides whether it is a elongated grain or equiax and so on, given by this schematic. These are the different regimes for the morphology factors, and the cooling rate will decide whether grains are very fine grain or large grains or elongated grains. So all these are plotted here. G is plotted as a depth of the melt pool. This R is plotted as a depth of the melt pool, and all these factors are plotted. And as you see that G is very high at the top and the bottom, and it is low, so you get a very fine equiax grains at the top and bottom, whereas elongated grains towards the in between, lower portion of the or lower to middle portion of the melt zone and so on. All these things can be predicted by these numbers. Also, as I mentioned earlier, if you plot the thermal gradient as a time, you get this kind of plots, and this can precisely tell you what transitions are occurring. These are the transitions up to the melting point. Then laser beam is moving, so this is material temperature raises, and then it melts here, starts melting here, and then laser beam still moving on, so it is moving away from the given point. So the liquid stop dropping the temperature, and this is a point, liquid stop dropping temperature, and then here it starts solidifying, and then temperature of solidification drops, and the change in slope of these curves gives the various transformation in the material, phase transformation. Especially in this case, there are solid state phase transformation you can see. So, and these are the specific points where the thermal gradient varies from one value to another values at different time locations, and then those are the locations you can precisely look at. Those are the locations where the various transformations occur, liquid to solid, solid state transformations. So all these things can precisely. So some of these transitions can be located on these locations, and those are such as formation of the precipitates along the grain boundaries, along the triple junctions, and so on. Composition contrast in the cell interiors. All those things can be predicted by this thermokinetic plots, plots of the different thermokinetic parameters as a function of time or the distance, and so on. So we have done quite a bit of in detail observation by using the techniques such as transmission electron microscopy and see whether these kind of plots, these kind of plots are predicting temperature, predicting various events during the thermokinetic process, at different locations like this. And they were indeed noticed through these observations. There are a lot of phase transformations occur in the H13 steel, and all these are given here, such as formation of martensite. Due to the high cooling rate, you get the twin martensite. Because of very high cooling rate, it cannot accommodate, in order to accommodate the lattice invariant shear during high cooling rate process associated. Because you look at the, go back here and look at the cooling rates. Somewhere I mentioned the cooling rates, very high cooling rates. Oh, sorry, here. These are the cooling rate. You get very high cooling rate you get here, and those cooling rates produce this kind of, this kind of microstructures where you get a twin martensites and so on. Also, such a high cooling rates also retain retain austenite. The martensite transformation not complete, and then what happens in a subsequent thermocycling due to the layer by layer deposition and multi-track deposition, you get the tempering of the structures and you get a carbide formation or dissociation of these carbides into benetic structure and so on. So all those things have been confirmed by these observations based on the TM. So ultimately, by model base, you can predict the microstructure, which can be verified by various experimental techniques, and you can get the required properties which are associated with this kind of microstructure development in the process and so on. So basically, all this can be interlinked together once you know the thermokinetics of the process. So another way I can say you that you can tailor the processing parameter such that you will be able to control the formation of these phases. Some of the phases you can avoid during the processing to get the required properties, as well as you can control the microstructural morphology, grain morphology, as well as you can control the crystallographic texture also, because I haven't gone into detail of that side, which involves quite a bit detail how you control the crystallographic texture of the material by controlling the thermokinetics of the process. So all this can be predicted as well as controlled by knowing the thermokinetics process through the computational modeling and so on. So we have been doing that to various processes, AM-based processes under our center. As you see that this is direct energy deposition process with a powder injection, which I talked about. Then there is a powder, there are powder bed process, where the powder is very stationary in the container and laser beam scans over the powder. Then this is a surface modification. You don't have to build the AM component from bottom up. You have existing component. On the top of that component, you can deposit layer by layer new material to build another layer on the top of the existing component to get the required properties, and so on. So all these processes will have different, and this is a solid state aim process where you are using friction stir welding process to weld the layer by layer material on the top of each other to get the component. So each one of these will have different thermokinetics, and accordingly you have to modify the equations to predict the thermokinetics of the process, and then accordingly predict the microstructure as well as the phase structure in the material. So all these things have been looked at in our center. Now this is for the, in general for the process, but also that varies from the material system to material system, because each material system has different properties, and some of the things will dominate in one system than compared to the other system. For example, high conducting material, low thermal conducting material, and high thermal conducting material will have totally different effects, different thermokinetics during the process, and different effects in terms of microstructure development. So you have to take into account those aspects in the AM process. So I think with this, I think I have given you quite a bit snapshot of how to approach this AM process to get a better control over the process for you to produce the components with the desired properties properties for the intended application of that component. I think with this I'll stop here, and if there are any comments or any questions, I'll be glad to respond to.
Thank you, Dr. Dahotre, for your very interesting talk. We are a little bit delayed in the schedule, so if you want to interact with him, he will be here with us so that you can, continue talking to him. And I would like to ask Dr. Patricia Zambrano to give the recognition letter. Thank you so much.
Thank you.
Thank you.
Oh, thank you very much. I appreciate that. Yeah.
It's a pleasure that you stay here.
Thank you. It's my pleasure to come here. Yeah. Thank you, guys.